Hello, children. Now we're going to look at how the evil dark side of the empire would solve something like number one from section 8.3 in a much worse way than the good that I did earlier. But we will check it out just so you have that information. And remember, I am not your father. All right, let's get going. So, I tried to do this earlier several times and it kept cutting me off and stopping the audio. But if you remember for section 8.3, number one, we were trying to figure that one out. We had literally the infinite sum from 1 to infinity of 1 over 2n minus 1 times 2n plus 1. And we're trying to figure out what the nth partial term is in terms of n. And by doing that, what we can do is we can take the limit as n goes to infinity of that nth partial sum and see if that exists and equals some value s, and then we would know that that would be the limit that the sequence would approach, and it would be convergent. So let's just go ahead and see how the book might do that. What they did, they didn't show any details, but definitely the patterns that we saw was much better. What we could do is we could say, hey, can we rewrite this using partial fractions? When we did partial fractions, we called that a over 2n minus 1 plus b over 2n plus 1. And when we do that, the power of the denominator for each one is n to the first power, so we just need an a on top. If it was n squared on the bottom, we would need a an plus b above it, if you remember that from partial fractions. But anyway, let's go ahead and work this out. We're going to go ahead and multiply everything through by the least common denominator, which is 2n minus 1 times 2n plus 1. And we're going to multiply that through here and on the right side, which has the distributive law. So what we end up with by doing that is 1 is going to equal the 2n minus 1's cancel there, so it's going to be a times 2n plus 1 plus b times 2n minus 1, because the 2n plus 1's would cancel. So multiplying this out, this is going to be 2an plus a, and then plus 2bn, so n is our variable, and then minus b. And what's that equal? That equals 1, but that's the constant term. So we also have, don't forget, we have 0n plus 1. Well, what are my n's? My n's are here and here. So the reality is I have two equations, two unknowns. If I factor n out, that's 2a plus 2b quantity times n. That's going to equal 0 on the left side here, because that's the coefficient there. And then we're also going to have, from the blue one, for our constant terms, a and b are constants, right? So we have a minus b equals the constant of 1. And so what we could really do here, now we have two equations, two unknowns. So I can rewrite that. The top one, I could divide everything by 2, and I end up with a plus b equals 0. And of course, it's equivalent to that. And then on the bottom, a minus b equals 1. So I have two equations, two unknowns. One of the ways, we could always use substitution, solve for one in terms of one of the variables, sub it into the other. But we could add equations here. And if I do that, I get 2a equals 1. And to solve that for a, says that a equals 1/2. And then if I substitute that in, say, to the first one here, 1/2 plus what is 0? B is going to equal negative 1/2. So basically I could, instead of a up here, I have 1/2, and instead of b up here, I have minus 1/2 times that. And then what I can do is I can factor out a 1/2. And if I do that, let's just kind of start over. So I can rewrite this 1 over 2n minus 1 times 2n plus 1 is going to be equivalent to 1/2 times the quantity, and that would be 1 over 2n minus 1 was what I had for the first one. I didn't have my screen up anymore, so I had to look at my notes. Plus, or actually plus a minus 1. So I'm going to put minus 1 over 2n plus 1. So you might think, well, that kind of looks the same. Well, it's not, because on the left side I have a product in the denominator, and on the right side I don't. So this is actually what a sub n equals. Remember, a sub n is the value of the nth term. That's different than s sub n, which is the nth partial sum. So what we want to do is we want to figure out what that nth partial sum is. But what I'm going to do is I'm going to utilize the right side here, and we're just going to look at what the first partial sum is. Well, the first partial sum, s sub 1, that's just going to be a sub 1, right? So that's a sub 1, which if I plug in a 1 here for n, it's going to be 1/2 times. If I plug in 1, I get 1 over 2 minus 1 is 1 over 1, which is 1 minus, and if I plug in 1 again, it's going to be 1/3. So I'm going to get 1/2 times 1 minus 1/3. I'm going to let you, that's 2/3 in there times a half is going to be equivalent to 1/3. So the first partial sum is 1/3. Okay, we got that before when I did it earlier, but let's look at the second partial sum. So if I look at the second partial sum, I'm going to do this a couple of different ways. Really what this is this is a1 plus a2, the first term plus the second term. So the first term we already have, is 1/3. So you know, we wouldn't have to redo that. But what I'm going to do, instead of writing 1/3, I'm going to help you kind of see the pattern. If I write this as 1/2 times the quantity, and this one is going to be 1 minus 1/3, I've got that in there. But now I'm going to say, okay, hey, what's the second term? The second term is 1/2, which if I have it factored out in front, which I do, it's right there, I don't need to worry about that. So I'm going to add on, the half is already there out front. So I'm going to go ahead and plug in 2 here. If I plug in 2, I get 1 over 4 minus 1 is 1/3. And then minus, if I plug in 2 over here, it's 1 over 4 plus 1 is 1/5. Okay. And once again, I have the 1/2 that's here is actually, because of the distributive law, is really attached to this as well. But I wanted to draw it like this because one thing that you might notice here is you might notice that there's some cancellation stuff going on here, because I've got a minus 1/3 here, and I've got a plus 1/3 there. And so really what happens is it's 1 minus 1/5 in the parentheses, which is 4/5 times a half, which is times 4/5 times a half is 4/10, which reduces to 2/5, which is what we had before. So anyway, this is 2/5, and we noticed a pattern: 1/3, 2/5. The next one was 3/7. The next one after that actually is 4/9. But once again, I'm going to do one more here. Use a different color. I'm going to do S sub 3. So really, S sub 3 is A1 plus A2 plus A3. Now we know that A1 is 1/3. So this is 1/3 plus A2, we already got, was 2/5, right? And then plus A3. So we can figure out what the value of the third term is. So if I do that, I'm going to do this underneath in purple, but the value of the third term, if I plug in 3 up here, it's 1/2 times what? Plugging in, that's 1 over 2 times 3 is 6, minus 1 is 1/5, minus 1/7. Once again, plugging 3 in there. So it's 1/3. So the third partial sum is 1/3 plus 2/5 plus whatever that is, which actually ends up equaling 3/7. Okay, but what I want to do is I want to rewrite this a little bit better. Anyway, this part right here is 3/7. Okay. Actually, no, it's not. That's not 3/7. The sum of all this stuff is 3/7. Sorry. So the total sum for S3, the third partial sum, ends up being 3/7. But if I did in here, what would I have to do? 1/5 is 7/35, right? And 1/7 is 5/35. So this is 2/35 times a half. So the 2's cancel. So this part in here actually is 1/35. Sorry. So anyway, I'll let you do the math. But if you take 1/3 plus 2/5 plus 1/35, you should end up with the third partial sum of 3/7, which we had before. But what I want to do is I want to rewrite this differently. So I want to rewrite S sub 2. We wrote S sub 2 like this, right? And then what I can do is use that with how I wrote A sub 3 here in purple, and start to see a pattern here. So I'm just gonna hope I remember all this stuff. But anyway, S sub 3, if I rewrite it, the third partial sum, if I had that 1/2 out front, then I don't have to worry about anything else. What am I left with? Well, if you remember, I think I did the first one in red. It was 1 minus 1/3, and then plus the next one I did in blue. It's 1/3 minus 1/5. That was for the second A sub 2, right? And then plus, I got to add the third one, which I did in purple. This would be 1/5 minus 1/7. Okay, and I'm just doing it this way for a reason, because what you notice, if we said, hey, it looks like stuff is kind of canceling out here. The 1/3s cancel, the 1/5s cancel, etc. This becomes 1 minus 1/7, which is 6/7 times a half, ends up being the partial sum of this equals 3/7, which was the value of the third partial sum. So the reality is, what I want to do then is I want to do this for the nth partial sum. I want to find out what S sub n is. So let's do that. So if I look at S sub n, remember sometimes when I write a small s, I like to use cursives. But anyway, it's going to be 1/2. We see a pattern going. And the first one is going to be 1 minus 1/3 from the first term, plus 1/3 minus 1/5 from the second term, and then plus 1/5 minus 1/7 from the third term, plus, now we can keep going here, it'd be 1/7 minus 1/9 for the fourth term, not the fourth sum, but the fourth term. Anyway, and I'm going to keep going, and I remember I'm going up to the nth one, so the value of the nth one. Well, the value of the nth one I'm going to write right here. I've got the 1/2 out of there, but we came up with our partial fractions was 1/2n minus 1, and then minus 1/2n plus 1. That is the value of the nth term. Now that in and of itself isn't very exciting, because you're like, well, what does all this add up to? So what we really need to do is figure out the one before this. The one before this would be S sub n minus 1. So if I plug an n minus 1 in everywhere there's an n, what this ends up being, if you noticed, the minus 1/5 and the 1/5 are the same. So the 1/2n minus 1 that I have here would also be here. 1/2n minus 1 would be there. Anyway, and then the one before that would be 1/2n minus 3. So it'd be 2 less than that. So if you notice 7 to 5 here, 5 to 3. So this is going to be 2 less than that one. So it's 1/2n minus 3. But anyway, so we're going to fill the gaps that way. But since I've been using green to cancel a bunch of goodies out that are all the same, the 1/5 cancel with opposite signs. The 1/7 minus 1/7 would cancel with a positive 1/7 over here. The minus 1 over 2n minus 3 would cancel with this positive 1. And of course, this minus 1 over 2n minus 1 would cancel with that positive 1. And so the question is, what's left? And I'll leave what's left in black. So S sub n is going to end up equaling 1/2 times, don't forget about that 1. This is still there. So we have 1 and then minus. The only thing that's left besides this 1 is this minus 1 over 2n plus 1. So we have this as the value of the nth partial sum. So that is in terms of n. It still doesn't match the answer in the book. So what could we do? We could get, of course, we could get a common denominator. I haven't used red yet, I don't think. So if I call this 2n plus 1 over 2n plus 1, that is equivalent to 1, right? So now this equals 1/2 times, the denominator is going to be 2n plus 1. And then on top, what do I got? I got 2n plus 1 minus 1 just becomes 2n. And then, of course, I could now cancel this 2 with this 2. And I end up with the nth partial sum, S sub n, is going to be equivalent to then n over 2n plus 1. So that's the value of the nth partial term, which is what we had before. Now, we noticed it by seeing the pattern that looked pretty evident of arithmetic sequences going on in the numerator and denominator for what we were end up getting for the first partial sum, second partial sum, third partial sum, etc. And that's actually what it is. So here is a proof that beyond shadow of a reasonable doubt, we rewrote it. This is where, you know, a couple people in class are going, hey, what's going on? How do we get to that formula? Well, you can recognize it. It can be from a previous theorem, like when we had the sum of the first n natural numbers, or sum 1 to n of n squared, or sum 1 to n of n to the third, or sum 1 to n of n to the fourth. We had those in a previous section. So if we have those formulas, we know it, but we actually developed this by either recognizing the pattern like I did in the first video, the Star Wars video, and of course this is The Empire Strikes Back. Which way is better? Obviously my way is better, and good is much better than evil in general. But we have this. So let me just rewrite this now as S sub n. The nth partial sum is n over 2n plus 1. Now the question is, what does that equal? What's that limit? So if I take the limit as n goes to infinity of this thing, limit as n goes to infinity of this sequence, of this partial sum, then we can see what that approaches. So that'd be the limit as n goes to infinity of the right side. Well, how do we evaluate that? We're going to divide each numerator and denominator by the biggest power of n, right? So in this case, just n to the first. Of course, dividing the denominator all by n means dividing each term by n because of the laws of fractions. But anyway, so this is going to end up being equivalent to the limit as n goes to infinity of, let's just use green for what cancels out. That cancels out to a 1 on top, and these ends cancel out to a 1. So anyway, it ends up being the limit as n goes to infinity of 1 over 2 plus 1 over n. And of course now, if I let n go to infinity, let n approach infinity, then this is going to equal, this part right here is going to go to 0. So this ends up equaling 1/2. And of course, what's that? What's 1/2? 1/2 is the sum n equals 1 to infinity of 1 over 2n minus 1 times 2n plus 1. So that was the original problem. So this series is convergent, and it actually approaches a limit of 1/2. So if you add up the infinitely many terms here from 1 to infinity, a sub 1 plus a sub 2 plus all the way to a sub n, plus you keep going forever, that ends up converging to a limit of 1/2. So there you go on that. So you know, the dark side is evil. Stay away from it, and go from there, and use the force, especially on May the 4th, and may the 4th be with you.